Okay,
Yeah,
now
it is not touching.
it doesn't like Roshan, this Google Meet.
I will inform to you.
Okay, I can share the. Okay, so
Join matter, ba?
okay, so can you see this?
Sir,
Yes, sir.
Can you see the screen now?
yes, sir.
Okay, so this is where we reached yesterday. Okay, so yesterday we are looking at Cauchy's method of steepest ascent. So this is the direction of steepest ascent. Okay, and under that is the projection on the xy plane, and this is called del f, or the gradient vector. So equation for del f is obtained like this. Okay. So partial f by partial x at x naught y naught is the x coordinate, and partial f by partial y at x naught y naught is the y coordinate. So this is del f. So this is this thing, okay, on the x coordinate, and this is on the y coordinate. So this is delta x or delta y, or sometimes we call it a and b. Okay, then we also saw that if the objective function is not symmetric about the z-axis, then if you have a starting point x naught, y naught, and you find the steepest ascent vector, it will not touch this global peak. Okay, it will touch some other point here, and then you have to change the direction. So what you see here is the schematic diagram of how the direction is repeatedly changed at each contours. And finally, after doing lot of zigzagging, you will reach the global peak. So now we'll do some simple example with what we have studied up to now. So for this objective function, can find the direction of the steepest descent minima at the starting point 2, 2. So starting point is already given, and first you can use the contours. Okay. So you have to draw the contour at 2, 2, and draw the tangent, and then perpendicular to the tangent. That's the direction of steepest ascent. Okay. So actually this method will not be asked for exam. This is just to show you the topology of the contours and all this. Okay, so this is the contours, and this is our starting point 2, 2. So if you look at the contour, minima is somewhere here. So you can see the blue region. So this is like minus 100 and all. So these are the blue regions. Minima is somewhere here. Okay, so we are now here. So what you have to do is that, as per our knowledge of graphical method, you have to draw this contour passing through 2, 2. Okay, and then at that point you have to draw the tangent. So where this point touches the contour, you draw the tangent and then draw the normal to the tangent. So normal to tangent can be both directions. This is ascending, this is descending. Okay. We know that this is descending because minima is on this side of the contour. So this is how you graphically obtain the direction of steepest ascent or steepest descent. And also by measuring this angle, you find alpha equal to 76 degree. That is with respect to the x-axis. Okay, so this angle is 76 degree. So now let us obtain the same thing without the graphical method. That is by using the equations. Okay, so now del f can be, that is the direction of vector del f can be found out from this equation. That is, you find partial f by partial x at x naught y naught. This is A, partial F by A, x naught, y naught. This is B. So, um, oh, oh. so, partial F by partial x at 2 is minus 2. Then partial y by partial f at 2 is minus 8. So this is actually steepest ascent direction. Okay. As per the formula, this is for steepest ascent. Okay, but we are going down. So you have to take negative of the steepest ascent direction. So it will be +2 and +8. Okay, so what is the meaning of the delta x is +2, delta y is +8. Okay, delta x is +2, delta y is +8. So this is the direction of delta. Okay, so you can see that this angle will be 76 degree. So I have drawn it here. So this is 2i plus 8j. So this is 2, this is 8. +2 +8. Okay. Okay, so this is how you find the direction of del F using computational methods. In practice, nobody will draw contours and all these things. Okay, then what is the elevation of the point 22? Elevation of the point 22 is the altitude of the point above or below the xy plane. So it is nothing but f of 22. So it is -4. So this point 22 is a distance of -4 from the xy plane. Then what is the elevation angle? The elevation angle is the tan theta is absolute value of f. So it is 83.13 degree. So gradient vector is like this. Okay, so steepest ascent or steepest descent vector is at 83.13 degrees above this gradient vector. So this is in the z-axis direction. Anyway, this is not important. Okay, this elevation angle is not important for our future use. Next, how to check for steepest ascent direction iteratively. So this is highly important. All algorithms in the future will use this type of logic. So in the general case, steepest ascent vector from one contour will not point to the global maximum. That is, if the objective function is not symmetric about the z-axis, the steepest ascent vector will just touch another contour at the maximum altitude along the path. Okay, so suppose you're starting from here x naught, y naught. So this is the steepest ascent path. Okay, so this del f is the steepest ascent path. Okay, so you are climbing the objective function like this above the del f vector. So you will reach A. So at A there is another contour like this. So after you reach A, if you further keep on moving, then you will come down. Okay. So the same point A is shown in the plan view here. Okay. So what you have to do is that you have to search for the maximum value of the objective function along the xy points of the del f function. Okay, so okay, you have to search for all these points. Okay, until you reach the maximum altitude, and there you find A. So that means you have hit another contour A, but you still have to reach here. Okay. Okay. So this is called line search. Line search means you are searching xy point along this gradient vector. Okay. Okay. So you are searching this slice of the objective function. So you are searching this slice of the objective function which is lying above this gradient vector. So that is the meaning of line search. Okay. So let us assume that you reached A. Okay, so now you reached A. So this is the plan view. Okay, Now you reached A. So it has hit another contour B. Now what you have to do is that at A you draw the tangent and then you again find the next steepest ascent vector. So this will um, okay. Okay. So again you find the next steepest ascent vector and it will hit another contour. It will hit this contour and then again you have to change direction. Okay. So ultimately you will reach the peak. So once a point A x1 y1 is located on the new contour, then search for the next steepest ascent from there. So it will touch another contour at B. And the procedure is repeated until the highest point is reached. So what you have to do is that you may have to keep on going like this until you reach the global maximum. So ideally it will keep on continuing till infinity. So you have to give a tolerance. At that tolerance value, it will stop. Okay, so this is how the Cauchy's method works. So let us see how it makes this search. Okay. Okay, how to conduct line search along the steepest ascent vector. So now what you have to do is that line equation, that is the del F equation, has to be expressed in the parametric form. So what is the meaning of parametric form? The parametric form means x and y are represented in one variable h. So before we go to this lines, uh, I will give another simple example. So this is the equation of a circle, okay, of radius r. So the normal equation and at center 0. So the normal form of the equation is x squared plus y squared equal to r squared. So this is not parametric form. Parametric form means both x and the y has to be represented based on a single variable. Okay, so theta is the angle. So any point here, xy, xy can be represented as x equal to r cos theta, y equal to, sorry, y equal to r sin theta. Okay, so x is represented in terms of one variable theta and y is also represented in case of one variable theta. So this is called parametric form. So if you put various values of theta like 1 degree, 2 degree up to 360 degrees, okay, then you can get various values of x and y. Okay, so x is equal to um, r cos, you can write 360 into h, okay, where h varies from 0 to 1. H is from 0 to 1. Okay, so this is parametric form of circle equation. So if you give various values of h from 0 to 1, you can get all the points of x along the circumference of the circle. And same for y. Y is equal to r sine 360 into h. Okay, so this is the example with the circle. So in the same way, many geometries like parabola, lines and all can be represented based on a single variable h. So this is particularly useful for certain situations. Okay. Normally we don't use parametric form, we use this direct form of the equation. Okay, so now let us go to the line. Okay. So in the same way, the equation of a line passing from say 1 3 to 2 6, line passing from 1 3 to 2 6 can be written as in the parametric. Just wait, one phone call is there. Yeah, I will say there are some reading. Okay, so I will take example of a line which starts from 1, 3 to 2, 6. Normally, we write the equation of the line as y equal to 3x. Okay, so let us see how it is written in the parametric form. So the same line can be written in the parametric form as x equal to 1 plus h, y equal to 3 plus 3h. So if you give various values of h, that is from 0 to 1, we will get various values on the curve. Okay, so if you put h is equal to 0, you get y is equal to 1 and x is equal to 1 and y equal to 3. Okay, and if you put h is equal to 1, you get 2, 6. And if you put h is equal to 0.5, then you will get the midpoint. If you put h is equal to -1, h is equal to -1, you get a point on the other side of the line. And if you put h is equal to 2, then you get a point here. Okay, so by giving various values of h, you can get various values of x and y without the need for the exact equation. Okay, so what is the method of getting this parametric equation of the line? So the formula for obtaining parametric equation of a line starting from x0, y0 and ending at x1, y1 is this one. That is x is equal to x0 plus x1 minus x0 into h. Y equal to y0 plus y1 minus y0 into h. So, okay, this x1 minus x0 is represented by delta x. Y1 minus y0 is represented by delta y. Okay. So this h can vary from like minus infinity to plus infinity. So you get all points on the line from minus infinity to plus infinity. Okay. Sometimes instead of delta x, they write x0 plus ah. Instead of delta y, they put y0 plus bh. Okay, so this is the line starting from x0, y0. Okay, so this is delta x. This is delta y. Okay. So if delta x and delta y is given directly, you can use it. Otherwise, they must give you the value of x and y1. So then delta x will be x1 minus x0. Delta y will be y1 minus y0. Okay. Okay. So in our example, if you substitute these things, okay, then you get this equation. That is 1 plus 2 minus 1. So x is equal to 1 plus h and y is equal to 3 plus 3h. Okay. So we can apply this in the parametric equation of the del f vector. So actually, we already saw that for this del f vector, this is b. This is b and this is a, and the value of b is partial f by partial y at x0, y0, and the value of a is partial f by partial at x0, y0. So you can directly write the parametric equation like this. So the del x into h, then del y into h. Okay. So this is the starting point. Okay, suppose this is starting at 1, 1. So this will become 1 plus a into h. Then this will also become 1 plus a into h. Then if you are going down, then you have to use the negative directions. That is minus a and minus b. Then procedure for conducting the line sum. So insert the line equation x equal to x0 plus ah and y is equal to y0 plus bh. So it's actually del f. Okay, del f direction into the objective function equation. So in the objective function, wherever you see x, you put x naught plus ah. Wherever you put y, you put y naught plus bh. So now f of xy becomes f of h. Okay, because all the x and y has been replaced with functions of h. So now f of h represents the points on the surface, but along the steepest ascent vector. Okay, so this is the objective function. This is the this is the contour. Okay, contour. So this is our starting point. X naught, y naught. This is the del f vector. Okay, this is the del f vector. Okay, so this is the slice of the objective function above the del f vector. So this is called f of h. Okay, f of h. And okay, so from f of okay, so f of h represents the points on the surface, but along the steepest vector. So you have to use only these xy points. Okay. Okay, so f of h represents the points on the surface, but along the direction of the steepest vector. So from f of h, find the optima, that is the maximum or minimum point h star. So you have to find this altitude where point where maximum height occurs. And okay, so here h is equal to 0. Here h may be equal to 1. Somewhere in the middle, you get h star. Okay, h star is the place where this maximum altitude occurred. So so this point is f of h star. F of h star is the peak. Okay. So once we reach f of h star, it means that we reach the next contour. If we touch the next contour. Okay. So then you have to repeat the procedure with the new contour. Okay. So now we will do it with this example. So this will be asked for the assignment and the quiz. And in the quiz and assignment, there's no need to draw the contour. It will be just done with the equations and calculation. So let us look at this question. Find the minima of this objective function and show two iterations. Starting point is given. X naught, y naught equal to minus 1, 1. Okay. Actually, just for your understanding, I am showing the contour. Okay. So when the computer implements this method of Cauchy's ascent, it cannot visualize any contours or anything. It has to blindly use the gradient vector formula using the A and B and all that. Okay, so let us look at this picture. So you can see the contours here. Starting point is minus 1, 1. So what you have to do is that you have to draw tangent here and find this vector here. Okay, this is the del f vector. And ultimately it will touch B. So first step is we have to find the coordinates of B. Okay. And then after that again you have to do some more searches. Okay. So first how to find coordinates of B starting from minus 1, 1. Okay. So okay, calculation of the descent vector at x naught, y naught, minus 1, 1. So what you have to do is that you have to find this A value is A value of the descent vector. Is partial f by partial f at x naught, y naught, that is minus 6, and partial f by partial f at x naught, y naught, that is 6. So this is for ascent. Okay. And you have to take negative of this for descent. So this will be plus 6 and minus 6. So this is the direction of the descent vector. This is plus 6 and minus 6. So plus 6 is like this, x is plus 6 is like this, then minus 6y. So it will look like this. So this is the direction of del f, and this angle will be 45 degrees. Okay. 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 So This is the equation in vector form. You have to convert the vector, the expression of minus del f in the parametric form in terms of h. So we use this equation. So x is equal to x naught minus this, this value, that is plus 6 into h, and y equal to y naught minus this value, that is minus 6 into h. So what is the value of x naught? X naught is minus 1 and y naught is plus 1. Okay, so if you do the simplification, you will get this equation. So this is the parametric form of the gradient vector. So x is equal to minus 1 plus 6h, y is equal to 1 minus 6h. So what you do is that in the objective function equation, wherever you see x, you have to put minus 1 plus 6h. Wherever you see y, you have to put 1 minus 6h. So you get f of h. Okay. And then you have to find the minimum point of f of h. So that is where it will touch the next contour. Okay. So as I already told you, so this is the objective function. This is actually f of h. Okay. So for steepest ascent, you have to find, you have to maximize along f of h, where it will touch the next point b. Okay. So in our case, it is steepest descent, so you have to minimize along f of h. So it will touch the next point b. Okay, so we got the okay, so substitute these things. So f of h is actually, okay, this is x squared 2y squared minus 2xy minus 2x minus 2x. So wherever you see x, you put minus 1 plus 6h squared. Wherever you see y, you put 1 minus 6h squared, etc. So you get f of h. Okay. So then you have to find the minima of this. So where the minimum value of h occurs, you can equate first derivative to 0. That is 360h minus 72 equal to 0. H star is equal to 0.2. Okay. And then you can back substitute it in this relationship, and you can convert the h value in the corresponding x1, y1 value. So this is a 0.2 minus 0.2. So this is the next point b. Okay. So this is very important. Okay. That is how to substitute the equation of the search vector into the objective function, and you get a equation purely in h. Okay. So we found the value of next location b as 0.2 minus 0.2. So 0.2 minus 0.2 has been reached. Now we have to do one more iteration. Starting from b, you have to do one more search until it touches c at here. Okay. So I think actual value of c is 1.4, but we'll see if we are reaching there. So for the next search, starting point is 0.2 minus 0.2. Okay. And you have to find this del f vector. Okay. So you have to repeat same thing again. So now for next iteration, we will not look at any contours or anything. Since you are familiar with everything, we just look at the equation. So second iteration, starting from x1, y1, 0.2 minus 0.2. Okay, you find this partial of partial x. Then you get positive values for ascent. Then you take the opposite sign for descent. Okay, so this is okay. So this is the vector representation of the descent vector. So you can see that 1.2, 1.2, 1.2, 1.2. So your del f will be like this. So this angle also will be 45 degrees. So what you do? So now this vector equation has to be converted to parametric form in terms of h. So you can use the same method where we which we used in the last slide. Okay, so here you substitute these values of for partial f by partial x and partial f by partial y. So the parametric equation of search vector is obtained as x is equal to 0.2 plus 1.2h and y is equal to minus 0.2 plus 1.2h. So now in the objective function, wherever you see x, you put 0.2 plus 1.2h. Wherever you see y, you put minus 0.2 plus 1.2h. And you can differentiate it and you find that smallest value of h, minimum value of h occurs at h is equal to 1. And if you back substitute it in these equations, you get the corresponding x1, y1 values. Okay. So if you put the x is equal to 0.2 plus 1.2h. Okay, so you put x is equal to 1, you get 1.4. So that is how you recover the x coordinate from the h. You have to do the back substitution. So you found the point C. Point C. Okay. Okay. Point C has been found. So this is the cautious method of steepest ascent or steepest descent. Okay. Then comments on the cautious method. So its initial progress is very rapid. It initially covers large distances. Later its progress becomes very slow as we near the optimum. Okay, so what happens is that, and also each search vector is perpendicular to the previous search vector. There is no shortcut. No, you cannot diagonally go from one point to another point. Also, only first derivative information is used. So let us look at how this thing. Initial progress is very rapid, but later its progress becomes small. Okay, so it is like this. First it will go like this. Then later it will get stuck by making small right angles like this. And each search vector is perpendicular to the previous search vector like this. Okay. So you can't go from here to here directly. Okay. That's not allowed. Okay, so what we can do is that we can, I think we can stop here, okay, because already it's 6:50 now. What is the time now? 6:50 or 6:45?
6:46.
Okay, then maybe another 5 minutes or 10 minutes we can study. So there's another method is called Newton's method. We already studied the one variable version of the Newton's method. This is actually two variable method. So here we use first and second derivatives to find the optima. The search directions will not be orthogonal. Okay, so the search vector may point more accurately at the optima. So that is advantage of Newton's method. It may be faster than this Cauchy's method, which keeps on making infinite number of right-handed turns. However, one disadvantage of Newton's method is that you have to find second derivative matrix also. That will take some time. Okay, so Newton's theory of Newton's method, it is based on the Taylor series expansion, which is truncated up to second derivative. So we'll understand the theory of Newton's method based on single variable problem, and later we'll just insert more variables and make it two variables. That is the easiest way. So using Taylor series approximation, we investigate the small region delta x surrounding x naught for the stationary point. So we start at x naught, and after so this is the x-axis. So in our search for the minima, let us assume that we have reached x naught. So now we stop here. At x naught we stop here. Now we make a small variation delta x. So now delta x is the variable now. Delta x is the variable now, not x. Okay, small increment delta x is the variable now. Okay, and let us assume that this minima occurs at one particular value of x naught plus delta x. Okay. So the absolute value of the coordinate is x naught plus delta x. Okay, because x coordinates are starting from here. But relative value is delta x. Okay, so at this point where the slope is equal to 0, we can write uh, d of f of x naught plus delta x by d of delta x is equal to 0. That is our rate of change of this objective function with respect to delta x is equal to 0. Okay, so now with the Taylor series expansion, we get expression for f of x naught plus delta x. So using Taylor series expansion, expression for that value is f of x naught plus f dash into f dash of x naught. That is first derivative at x naught into delta x plus 0.5 into second derivative at x naught into delta x squared, etc. So this is the Taylor series expression for this numerator. Okay. Okay. So here delta x is the variable. Okay. Delta x is the variable, not x. Okay. So now let us do this this derivative. Okay. That is d of this term divided by d of delta x. So naturally, this will become 0 because this is the constant, and then this will become 1. Okay. So d of delta x by d of delta x is equal to 1. This will become 1. Okay. Then so d of delta x squared by d of delta x is equal to 2 delta x. So this will become 2 delta x. Okay. So after you can equate it to 0. So okay, so this has become 2 delta x multiplied by 0.5. So this 2 and 0.5 will cancel each other and we get only delta x. So it will simplify to this. Okay, so you can take delta x to one side and you get delta x is equal to minus of first derivative at f of x naught divided by second derivative at f of x naught. So this is the formula we used in a single variable Newton-Raphson method. Okay, method. Okay, so that time we did not do this derivation because I wanted to do it at a later time. So at this value of delta x, the slope will be approximately equal to 0. That is one thing. The secondly, because of the truncation at the second derivative, Newton's method works exactly for quadratic function. Because in a quadratic function also, you can get only up to second derivative. Third derivative, fourth derivatives, and all become 0. So if you have a quadratic objective function, this formula will work exactly well because it fits with the Taylor series truncation. Then the Newton's method will only find the stationary point. So, okay, so it can be either minima or maxima, and later you have to do further test at your own expense if you want to check if it is maxima or minimum. So I think we can stop here. Okay. So next class we see how this is extended to 2 variables. Okay, so I'll take some attendance now. Take attendance now. Stop this call.
பண்ணியாச்சு இது ஒர்க் ஆகுதா டியர்